Okay, so the last topic is quadratic, the square function, and the next one is a step up to quadratic polynomials. So the square function is a particular case of the simplest case of a quadratic polynomial, and then generally quadratic polynomials produce all of these. They have extra degrees of freedom, and those A, B, and C are those degrees of freedom. So there's a bunch of infinitely many quadratic polynomials. They all determined a lot of their behavior determined by those three parameters. The only thing that we wanted to be careful here that we do not want A to be equal to 0. Otherwise, if A equal to 0, then what do we get?
0.
Yeah. So if A is equal to 0, what kind of function is it? No. Look at the formula. A is equal to 0. The first term disappears. What is it?
Is it the line now?
It is. You're left with a linear polynomial. So a quadratic polynomial turns into a linear polynomial if that first coefficient A is equal to 0. Okay, so we wouldn't want to mix them up. So we'll say let A is not equal to 0. In that case, the graph will be once again a parabola. So if A is not equal to 0, if A is equal to 0, then you have a straight line. Otherwise, A is not equal to 0 every time. The behavior is very, very similar. And besides, we also don't divide by 0 over there in the quadratic formula. So what does the quadratic formula give us? In case you don't remember, it gives us the what does it give us?
X.
What?
It gives us X. Is that
You have to explain what you mean by that. So what's the meaning of the quadratic formula? It is x, yes. In fact, sometimes this is how you write it sometimes. X comma 2 is equal to this. Why is it 1 comma 2? Anybody? It is what? No. If you mean ordered pairs as point on the xy plane, then no. X1 sub F1 comma 2. What does it mean?
Like if you have two.
Two what?
Like 2 points.
It is 2 points. Yes. So okay, so that's why 1 and 2, and we have 2. Why do we have 2? Likely because we have plus or minus. Plus gives you 1, and minus gives you the other. Okay, but what are they? I didn't plot the graph of the function. I started and then I didn't. So what is that? Where are those x1 and x2? Well, they first of all they are probably on the xy plane. They are x's on the x axis. They are x's. And what's the meaning of them?
Where they cross the x-axis.
Yes, that's right. And we have a word for it. X-intercept, yes. So 2, but doesn't have to be 2. Remember that you have 2 because you have plus or minus, but it only gives you 2 when whatever follows plus or minus is not 0. So when this thing is equal to 0, this expression over here, if it is equal to 0, then you have only 1. Okay, so it is a possibility then you end up with the graph. So how can you possibly have only one x-intercept? Can you imagine? What does the graph look like? So it has only one x-intercept. No, it's still a parabola. Yeah. So that's right. So the also known as the vertex, and the graph touches the x-axis. Okay, so this is when b squared minus 4ac is equal to 0. You have 2 when b squared minus 4ac is positive, so that you have two values that follow plus or minus. So this is the plus or minus, which might produce two values, and it does when the this expression is positive. When it is 0, you have touch, one X-intercept. And what's the last case? What's the last case? There are no X-intercepts. And b squared minus 4ac is negative. Okay, so which means that square root is undefined, and there are no X-intercepts. So you try to solve an equation, and the equation being ax squared plus bx plus c is equal to 0. Solve this to find the X-intercepts. And you might find, depending on a, b, and c, you might find 2, 1, or none. Graphically, there these three cases are right here: 1, 2, and 3. So 2, 1, and none. Okay. Anybody remembers what this expression is called? Denoted by D often, which stands for, nobody remembers the word? The discriminant. So if you want to, the only thing you want to know is how many X-intercepts the parabola has, all you need to look at is the discriminant, b squared minus 4ac, and then depending on its sign, positive, 0, or negative, you will know. Okay, so once again, 2, 1, or none. Okay, so once again, if we try to repeat the analysis of the square function applied to this, everything is very similar, and it is easier to describe with the way I have. That's just to say the graph is a parabola. Okay, so if you know what the parabola looks like for the square function, we did a thorough job with it, and we know what roughly it looks like. Remember, it goes up, down, and then up. It has symmetry. It has no gaps. It has no cusps or anything like that. So that all of that we have learned applies to quadratic functions or quadratic polynomials. And the only thing that new is well, first of all, it does not have to be located symmetric relative to the y-axis. This is the y equal x squared. So it is located symmetrically, but other than that, it is in comparison to the quadratic functions that we're looking at, the location is special, but otherwise it's roughly the same shape and the same characteristics we can see with the graphs on the right. So they still have, no matter where they're located and whether they have X-intercept or not, there's an axis of symmetry. Okay, so we certainly were going to discuss that at some point. There is a formula, and that came for the point in the middle for the x's, which incidentally also gives us the minimum value right there. And we did that job early in this semester. Remember how we did it? Remember the problem about the farmer? The function was quadratic. The area in terms of the width of the enclosure. Remember that? It was a parabola. It was upside down. Okay, so we'll get to that. But other than that, it looks very similar to the graph on the right. So it has two X-intercepts. And then we found, how did we find the minimum value, or rather the maximum value? What? Yeah, but then, no, we did a better job of it eventually. We used the symmetry. We use the symmetry because the axis is, if it is symmetric, then the axis is in the middle between the two X-intercepts. So remember, it was 0 and 50. And then that's how we knew that the best choice was halfway, 25. So similarly, this is halfway to the left and to the right. The axis of the parabola lies halfway between the two x-intercepts, and that's how you can find it. Okay, so the axis is x equal x1 plus x2 over 2. So that's the axis is a straight line. So that's something that we have talked about just recently. The axis is a straight line, a vertical straight line, and vertical lines are given by the same type of equation: x equal 1, x equal 2, and so on. All of these are vertical lines. This one is particular. So we find where it crosses the x-axis. It crosses the x-axis halfway between x1 and x2, and that's how we find them. It is the average, right? So halfway between x1 and x2 is the average, x1 plus x2 over 2. So we easily found that way. If we know the x-intercepts over there with the quadratic formula, we can also find the vertex, and therefore we can find the minimum right here, right? If we can just do that. That simplifies fairly easily. If you, well, let me carry this out. So simplify. So x, well, that expression, x1 plus x2 over 2, let me take my quadratic formula over here and substitute first plus, then minus, and we'll see what happens. So these are the two different values. So it will be negative b plus the square root of the discriminant, okay, plus the other one, negative b minus the square root of the discriminant, divided by 2. Okay, makes sense? So I'm using the quadratic formula. I don't really care what the discriminant is, and that is why I don't want to actually write what the expression is. I just use so this is my d, the discriminant. B squared minus 4ac. Okay, so why I don't care, you'll see in a moment. Negative b plus square root of d minus b minus square root of d. So you see what happens?
Wouldn't the discriminant be canceled out?
It cancels out, so it doesn't matter what it is. Even if it is, even if when it's undefined, it's still canceled out. And then I have I'm sorry, I've missed an error here already. Yeah, I missed like this. Okay, that's better. So so every expression, maybe I just was rushing too fast. Let me make it do it more carefully. So over 2a over 2a. These are the two x-intercepts or roots of the polynomial. Okay, I add them together and divide by 2. Okay, then I do common denominators. That's how I have 2a. Okay, then I cancel d, and what I end up with is negative b over 2a. Okay. So the vertex is, so the conclusion is the vertex or the axis of symmetry of the parabola y equal ax squared plus bx plus c is x equal negative b over 2a. Once again, a is not equal to 0. So that's a theorem that we can appreciate because it really it tells us a lot about parabola, so that we don't have to do a lot of work in order to understand what's happening. We know where the behavior changes to the opposite. So it was going down. At that point above x, it starts to grow up again, unless of course it's the opposite. unless it's the opposite, and that is the next issue to be addressed, is the under what circumstances the parabolas might be upside down. That example that we had a parabola upside down. So it is a parabola either opens up like these, branches going up, or it opens down like that. Okay, so it is really not a big challenge. So this is what I'm talking about. The algebra certainly applies. The same algebra. So the quadratic formula applies. The X-intercepts will be still there, possibly like this, right? And then these are the two X-intercepts. Oh, if any, it could still touch like this and have only one X-intercept, or it could have none like that. Okay, so all the three possibilities are still there. What determines these two different behaviors? It's value of a, the coefficient in front of x squared. So the one that we looked at initially was a positive over here, and when a is negative, you have a parabola branching down. It suffices just to confirm that. Just compare y equal x squared and y equal negative x squared. Okay, you can see the symmetry. You can just plot them, and you can see how one appears above the other. Right. So if I'm plotting y equal x squared, it looks like this, which we already have done. Okay, and then where the values come from? Let me maybe move this away for a moment. Okay, so if I plot, if I make up two tables side by side, x and y, -3, -2, -1, 0, 1, 2, 3. Okay, the values are positives, the squares, 9, 4, 1, 0, 1, 4, 9. If I go with the other one, I have the same inputs, but the values will be the same but negative. -2, -1, 0, 1, 2, 3. The values of y will be -9, -4, -1, 0, -1, -4, -9. Okay, so they are aligned horizontally on purpose because I want to compare each of them because they will be paired up. So for example, -3, 9 is paired up with -3, -9. So for that's the point I might be talking about. This is -3, and this is 9. So that is the point of the original on the graph of the original function y equal x squared. But now where is the other point, the other pink point on the right? -3, 9, where is it?
-3, -9.
No, yeah, -3, -9. -3, -9, where is it? On the graph. Yeah, same, horizontally the same, but vertically goes in the opposite direction like this. Okay, so how far? Up to -9. So that is the opposite point on the graph over here. Okay, so and then every single time the same thing will happen. Say I pick say -1, 1, this point. So the point is over here. This is -1, this is 1, okay, and then once again I can find the counterpart on the graph of the new function, which will be once again horizontally. The x coordinate is the same, y coordinate becomes negative. So this point corresponds to that point, okay, and on and on. Every single time, what happens to the point on the graph that I pick on the graph of my original function? That's what it does. It flips. We already know how to describe this. If I now plot the other graph made of those points, no, the reflection is the word. So this is the second graph is the mirror image of the first. Okay, so literally once again, you draw the graph of y equal x squared on the piece of paper, and then you put the mirror. Where do you put the mirror? Yeah, you put it on the x-axis like this, maybe. So this is the mirror, and the reflection of the original graph, the green one, will give you the location, the shape of the new graph. So in other words, it's mirror image, not just mirror image, but mirror image relative to the x-axis. Okay, so exactly the same shape, just flipped upside down. Okay? So that is the major approach to studying functions. It is start with the function that you know, y equal x squared, and then discover more and more functions through symmetries or through operations, reflections, for example, translations, shifts, and what else? Translation, shifts, and rotations, as well as stretches. So that we'll see later. But for the time being, this is sufficient. This is just one example of how it is done, producing more and more functions and more quadratic polynomials. So it is A that will determines the directions of the branching, up or down, but it also determines how thin your parabola is. Okay, so one more step in that direction, and that is y equal x cubed. Okay, naturally, once again, how do you compute this function? You take x, make 3 copies of x, multiply by themselves. That's all by themselves. That's the output. Okay, it might represent the cube of the volume or cube of side x, for example. Okay, what about the graph? Well, let's start with the domain as always. Domain is everything. Okay, but the graph looks quite a bit different from the quadratic polynomial and the quadratic square function, and that is the symmetry is different. Okay, so once again, y equal x squared. Well, I guess maybe I could just take. Let me take this and see what the difference is. So you can see it easily from the graph, from the table of values. So if now, instead of looking at x squared, I will look at x cubed. Look at x cubed. Okay, so I'll put. No, maybe not. Let me start over. So I want to look at the table, and the pattern will be different. Remember, the pattern for x squared is it starts to repeat its values in the opposite order. So -2, -1, 0, 1, 2. What's going to happen is 4, 1, 0, 1, 4. As you can see, that's the symmetry, right? It starts to repeat itself. What happens with x cubed is quite a bit different, because when you multiply negative number by itself, you get the positive number. But if you take third power, what happens? -2 cubed. It's still negative, yes. So that's the crucial difference. So -2 cubed is -8. -1 cubed is -1, 0, 1, and 8. So there is, I cannot make those arches there to indicate the repeated values because there are no repeated values. So there is no repetition. Unlike x squared, x cubed has no repetitions, and so if x squared has this, both -1 and 1 end up at the same value, which is 1. Okay, that's not going to happen with third power. Okay, so remember what it means graphically for x squared. It means that the graph will have the symmetry. So this is my x squared. Okay, and then what we discover is this. This is -1. This is 1 and this is 1. As you can see, these arrows indicate how we compute the function. From -1 to 1, starting on the x-axis, started -1, we end up at 1 on the y-axis, right? And similarly, if we start at 1, once again going towards the graph, and we end up at 1. So they meet at the same point. If that's not the case ever with x cubed, it means that there won't be a horizontal line will never have two intersections. Okay, so that's the thing about x squared. Horizontal lines will have two intersections unless they're below the x-axis, but not so with x cubed. This is what it looks like. So once again, no vertical lines have two intersections. One intersection only, because there are no repetitions. Okay. Once you plot a few points, as I did, you start recognizing patterns. Okay. So what is well, we know the domain. We know you can see the growing values of y as x proceeds from left to right, like this. If x doing this, then what is y doing? It's going up. Different from x squared, which changes its pattern from down to up. Okay, so this one will keep going up. Then what we discussed last time, what about symmetry? So the symmetry on the left, we already know what it is, the mirror symmetry. What about the new one? Does it look symmetric? No? Does it look symmetric to anyone? Does it have some kind of pattern, repetitiveness to it? And once again, look at the two branches. Let me remove these red lines so that it would be in the way. I intentionally do it one branch at a time.
The same shape, but one's pointing in the positive direction.
And the other the negative. Okay, can you think of a way how you can transform one into the other? If it seems to be the same shape, then how do you transform it? Well, anything. What do you think? Does it look like a mirror? Where would you put a mirror? Well, yeah. Well, let's explore that. Is there a mirror symmetry? If it is a mirror symmetry, then you should be able to see one branch in place of the other. If you put the mirror in the right spot, where would you put a mirror? You have to put a mirror somehow between them. What's the angle?
On the y-axis.
No, if you see on the y-axis, we already did it. You'll see then the right branch will be to the left, like this. This is the mirror symmetry. If I put the mirror on the y-axis like this, then the right branch will be to the left, but not at bottom, but at the top. Right. So in other words, you do not transform the graph into itself, which is what we want. How do I transform one branch, the upper on the right branch, to the left bottom?
Rotation?
That's right. So what's the angle?
180?
180. That's right. Rotation 180, like this. Mother. Okay, rotation 180 degrees. Okay, so so that you would believe this easier, there is a Paint does it. Paint. It has all of these operations, so I could just as well do it. Okay, so let me try to do that. So if I have my axis, like this and like that. So let me start with a parabola. So this one is not going to be a parabola anymore, right? So it's not very thick. Can you see it? more or less. Okay, so this is what I can do with it, is this. So I highlight it, and then there is a rotate option here, you see, and then I have 5 possibilities. I have a rotation 90 degrees left, right. I have 180 degrees, which is what we're going to do, and then we have 2 flips. So right now, this is x squared. What do I do to find the symmetry? Flip horizontal, right? Flip horizontal. It should produce the exact same shape. Okay, same thing, right? You see? So I could go back and forth like this. It is more or less the same shape. It shifts a little bit, but it's the same shape. Okay, so let's do now x cubed. The same axes, just for reference. Okay, and then I plot my curve. Now I want to figure. Get this one. Okay. Okay, so once again I do this. Okay, so what do I flip? I flip 180, right? Okay, you see what happened, right? So I can go back and forth. So there is a certain shift, and my drawing wasn't perfect, but you can see that that roughly the shape remains the same. Okay, so that is a 180-degree turn, produces the same shape. Another way to see the symmetry is it is sometimes called the central symmetry, because you can go through the center like this roughly. Okay, so every point on one branch will produce a point on the other branch in this manner. So one point, here's another one, like this, and on. You can have as many points as you like in that manner. Okay? Okay, so this is symmetry. We'll talk more about symmetries later. This time we'll just we'll take a broader look at the power functions. So power functions are okay. Not good. Functions. So in other words, it's this list of x squared, x cubed, x to the 4th, and so on, x to the 5th. So a whole bunch of functions, and they exhibit a similar behavior, which we're already taking care of. This is straight line 45 degrees. This is a parabola upside down. This is a cubic thing that we just saw. And then what x to the 4th look like, roughly? Straight line, parabola, this kind of thing. What does x to the 4th look like? But what kind of symmetry do you think it has? 4th power, think about it. 4th power, so you multiply number by itself 4 times. Say, if I take -1, multiply by itself, what do I get?
Positive.
Positive. So what kind of symmetry you think? It is more similar to x cubed or x squared?
X squared.
X squared. So it has a kind of parabolic behavior, even though the bottom is flat up. The 5th degree, once again, has this kind of a growth. Well, that's not fair. I have to do it like this, like this. Okay, there is a picture here. Just here, should be here somewhere. This is the list of slightly nicer plotted power functions of degree 1, 2 through 6. As you can see, the odd powers are in the first row, even powers in the second row. The similarity of symmetries is noticeable, right? So the first row has the central symmetry, or rotation 180 degrees around the origin, or you have the mirror symmetry in the second row. Either mirror symmetry or folding of the graph about the y-axis. Okay, the difference also is noticeable. You can see how as the power goes up, you can see what's happening to the shape. Even though it is, you still might be tempted to describe it as a parabola, the bottom, second, and third, you can see how the bottom is flat. So the parabola, the true parabola is on the left, bottom left. Okay, so even though it is somewhat flat, or there's a peak there, but it is a fairly pointy peak. Okay, even though there is no corner there, but it is somewhat pointy. But the other two are flat. Okay, so that's how you should be able to tell the difference, and that's what happens as degree of that power goes up and up. It is early when the number is very small and you multiply by itself by high degree, then it is growing, but very, very slowly. So that's what I have to say here, is that x to the n, where n is a positive integer, called the degree. Okay, so then later on we'll see more and more of the stuff when with not just the powers of degrees, all imaginable degrees, but also the polynomials of each degree will appear. So if you compare the x squared compared to ax squared plus bx plus c, okay, so the complexity increases even though the shape of the graph does not. What happen, and then you can have the same build a polynomial for each of these degrees, and so then once again the behavior will be more complicated, and the shapes of graphs change once again. The rough picture does not change, but it could do this. X cubed, the cubic polynomial might look like this. It does not necessarily have this flatness, nor the symmetry might be as obvious as we saw before. So things become more complicated. Okay, so this is the rough idea. As there are more and more functions, we can have only like a glance view of what they look like. So like a bird's eye view of the functions and where they go in and how the complexity develops and whatever patterns are still visible. So this is one of very nice patterns is the symmetry. The symmetries, as well as the flatness of the bottom or speed of the growth, is what tells you one power from the other. Okay, so one more, and that is one more class of functions, reciprocal powers. So not entirely new. So we can just take power function and take its reciprocal. 1 over x, 1 over x squared, 1 over x cubed, x to the fourth, and so on. Okay, so they will still have certain symmetries, and the 1 over x will tell us most of the story. The main thing about f of x equal 1 over x is in contrast to everything we've seen so far, it is the domain. So domain is, what's the domain of this function? Yep.
All numbers except 0.
All but 0. That's right. So you're welcome to describe it this way in the form of a sentence. So I have no problem with that. Or you can use the set building notation. So it will be x not equal to 0. Also very nice. Same thing as I say there. Say x capital maybe. But in the more compact form. That's the only difference. And then there is the third way to put it, and that's with the help of integrals. So I'm using the integral notation. So from negative infinity to 0, and then from 0 to infinity, 0 excluded. Okay? So all are good. Okay. Now let's quickly plot it. Well, or not, maybe not so quickly. After we have a division. So let's see. So this time the domain is broken into two pieces. So you'd better have that explicitly seen. So I'll put 0 here like this. Make sure that I'm excluding these values, and then I have values that less than 0 above, and then below the next of them. So I'm going with the list, and once again I'm going -3, -1, -2, -1, 1, 2, and 3. Same values, but this time as for x squared, x cubed, but this time 0 is missing. It's outside the domain. Okay, take the reciprocal, -1/3, -1/2, -1, 1, 2, and 3. Okay, so based on this, on this data, you can tell, maybe predict the symmetry. If any. Does it? I'm sorry. Yeah. Thank you for not noticing. So it's 1, 1/2, 1/3, 1/2, 1/3. Okay, so So as you can see, if you try to match up these things, say -2 and 2, then look at how the values match up, the outputs. So the inputs are matched up, 2 and -2. The outputs are matched up also in the same manner with the negative number. Same with -3, negative. So negative remains negative. Why? Because it's x. So there is nothing for us to worry about as far as the squaring is concerned. So these are the matches. The symmetry, where does the symmetry come? So that's the symmetry, the matching up, pairing up of the values. And where does the symmetry comes from? It comes from here. Y equal x squared has a certain symmetry. I'm sorry, y equal x has a certain symmetry, and it conveys its symmetry to the new function. So y equal x is simply the diagonal. What kind of symmetry does it have?
Does it have mirror symmetry if you put it?
No, it is rotational symmetry. Diagonal going like this, so you rotate 180 degrees. It's still the same curve like this, right? So if this is your straight line, you rotate it 180 degrees, and it's the same line. Okay, so then the idea, if you take the reciprocal of the symmetry, is preserved. But let's discover that by plotting things point by point. It is only 6 points this time, so I'm plotting it -4 and -1, -2, -3, 1, 2, and 3, and the values are somewhat smaller, so I'll try to make it slightly disproportional. So it is -1/3. Say, how about this is 1? How about this is 1, 1, 1, 2, 3. -1, -2, -3. So on the x-axis, the units are smaller, just for our convenience, so we can see what's going on. So I'm plotting the very first point is -3, 1, -1/3. So I'm here somewhere. The first point, -3, -1/3. The second point is -2, -1/2. It's over here. And finally, the -1, -1. It's here. Okay, and then everything else is in the bottom half of my table. Everything is symmetric. So 1 and okay, let me put another mark here. So it will be 1 and 1, 1, 1. The point is 1, 1. Then it is 2 and 1/2, and it is 1 and 1/3. 3 and 1/3 over here somewhere. Okay. So that's my graph. The 6 values might not be sufficient to guess what the pattern is like. But imagine, just take the ones on the right. You can roughly imagine how this will continue. How will that continue? I take 3. Our next one is 4. It will be 4 and 1/4. 4 and 1/4. Then it will be 5 and 1/5. And so on. So what kind of pattern is this? So we are walking left, right, towards the to the right, okay, and equal step at a time, 1, 2, 3, 4, 5, and then what's happening to y's, the outputs. So these are y's.
Are they decreasing?
They're decreasing, yes, they're decreasing, but not really that fast, are they? So they are decreasing, right, but not past 0. They will never reach 0, right? So it will be 1/6, 1/8, and so on, but they will be getting smaller and smaller and smaller, but slower and slower and slower. So you can imagine what's happening is something like this. Okay, so then if you try to imagine what the whole thing looks like, that's roughly how you try to connect it into a single piece. Okay, and furthermore, once you understand the symmetry, you have that on the opposite side of the graph, it will exhibit the same behavior, only going towards the negative direction. Okay. Okay, so what remains is what is remaining here? What's left of the graph that we haven't taken care of?
As it's approaching the y-axis.
Approaches y-axis. So and it is important. We did not have to do it when we did x squared because it was 0 at 0, so we knew where to go. And this time we have to approach the y-axis, but we have to approach it very carefully. We cannot jump to it because the function is undefined. So we'll have to insert values here, right, in order to either